know, this semester I've been doing an independent study where I've been self-teaching myself basic particle physics and researching how a certain particle detector works to probe the subatomic world. So today I'll be telling you all about some of what I've learned about what lies below the atom. So there's a question of what is fundamental. This question has motivated people since the beginning of history to look deeper and deeper to understand what really makes up our world. An ancient Greek philosopher, Democritus, thought that it was made of tiny, indivisible particles he called atoms. And his theory wasn't completely wrong, and it lasted over 2 millennia. And so this question continues to motivate people today, including myself, to just look deeper and deeper. Through a lot of experiments and theorizing, chemists and physicists gradually discovered that those little atoms weren't indivisible. They were made up of a positive dense center with protons and neutrons, and with a cloud of negative particles surrounding it called electrons. And this model is what's in the minds of most people when they think of what's the most fundamental thing. And it's not completely inaccurate. Most chemical processes can be explained using just this model, but it's not fundamental, according to what we know today. So in the early 20th century, a ton of new particles were discovered, and they didn't really fit the profile of what chemists and physicists thought made up protons and neutrons. They were different, and so maybe that started the theory. Well, maybe there's something else inside of them that's making that's even more fundamental. That's making these other particles. So with a bunch of experiments and a bunch of theorizing, a standard model emerged, which is a mathematical and physical theory of the most fundamental particles, and also describes the forces that interact with them, or that they interact with. This model was confirmed in the 1970s with experimental verification of a lot of the things that it predicted, but it wasn't in the 1970s that they found all of them. So with faith in their model, physicists went looking for more, and looking, and they found them. In 1995, they found the top quark, which was one of the fundamental particles it predicted. In 2000, they found the tau neutrino, another particle they predicted, and even as recently as 2012, they found the Higgs boson, which is a really complicated one, but it's really exciting. But this is, again, not to say that the standard model solves physics. As we've had experiments and new knowledge, the model has been tweaked and adjusted so it grows as our knowledge does. So this is the Common diagram outlining the standard model. Here you see all of the most fundamental particles that make up our world. Notice the structure of it. The structure of it is very important, just like the structure of the periodic table is very important. And the different colors in this diagram represent different things. So I just want to say quickly that the mathematical theory that governs all of this is extremely complicated and was created by the greatest minds in our time, and parts of it still baffles them. So we cannot be expected to understand all of the math behind it. But from that math emerges properties that we assign to model them. But these properties are not so concrete and not so logical as we would like, because that's not how the math works out, and that's not the behavior that we observe. So just be okay with not being comfortable with it. So let's dive in. So these are quarks. There are 6 different types of quarks, or as physicists call them, 6 different flavors. Flavors just means type. They like to make things funny. Like, as you can see, this is the charm quark, the strange quark. Like they you know. So all of these quarks have some of them have common properties. They all have a 1/2 spin and a fractional charge. The top row has +2/3, and the bottom row has -1/3. But they have significantly different masses. Like you can see even in the units, this is mega versus giga. Like it's crazy different masses. And even though they're very small, it's a big margin. So quarks never exist alone in today. They always will combine to form a hadron, which is just a particle that is made out of quarks. And in a way that the electric charge will be an integer number. So the proton is actually made up of 2 up quarks and 1 down quark. So it has 2 plus 2/3 charges and 1 minus 1/3, and that equals plus 1, the charge of a proton. So next are the leptons. These are, I should say that that quarks make up most of what we think of as matter. Leptons also make up things that we think of as matter, as massive objects, but they're kind of weird. They have mass, but they don't have an internal structure. This is where the weirdness comes in, that it's how the math describes it, and using this model, it predicts results that are like right on. So it's weird, but it works. So the electron, our good old friend, the electron, is actually one of the most fundamental particles that we know of. So again, like quarks, there are 6 different flavors, 3 with significant mass on the top row, and the neutrinos on the bottom row, which have like just a tiny, tiny little bit of mass, but they're super common. They're actually always coming through the planet, but they are so elusive, they don't like to interact with things, that they can pass through the entire planet without touching another single atom. So that's how tiny and how much they don't like to interact with things. So next these were all of the particles that make up massive objects. But there are also particles in the Standard Model that don't make up objects. They are force carrier particles. So we all know that there are 4 fundamental forces. But it would actually be more accurate to say there are 4 fundamental interactions. This is because forces are actually at this level just fermions, the massive particles, or the particles that make up mass, passing these bosons to each other and thus creating an attraction or repulsion. So instead of going boson by boson, I'll go by forces. We all know the electromagnetic force. It's friction, it's magnetism, it's electricity, it's the normal force, all attributed to this fundamental interaction. So the photon is its force carrier boson. So what happens is that fermions, which were the particles I talked about before that have electric charge, will pass photons to each other, and thus creating a attraction or repulsion. The mechanisms behind this are really complicated, and I'm not going to go into that today, but that's how the math works out, and that's what's really happening. And we'll see that a little bit later. Next is the weak force, which is not one that we see every day, but it's responsible for why particles will decay. And it actually has 3 carrier bosons. The Z boson, which is this one, and the W boson, but there are 2 different types of W bosons. There's a positively charged one and a negatively charged one. And something interesting about the weak force is that at really, really high energies, like Big Bang, like when the universe was really young, the same mechanisms and principles that describe the electromagnetic force can also be used to describe the weak force. And so in this way, physicists have unified these 2 forces into the electroweak force. So next I'll talk about the strong force. And the strong force's carrier boson is the gluon. So to describe the strong force, I have to introduce a concept called color. So let's go back to electric charge for a second. We all know electric charge. But fundamentally, electric charge is just a model that describes the theory of electromagnetism and the behavior that we observe. So color charge is like this. You could say that a quark has like a red color charge, a blue color charge, a green color charge. It's not that they actually are these colors visibly, it's just that this model describes the interaction very accurately. So quarks, like I said, they will always combine into hadrons, and this is because they always want to be color neutral. So they want to have like 3 complementary colors. And the way that they achieve this is by constantly passing gluons to each other. And so I have a quick video to visualize this process. So before I start it, this little dot right here is the gluon. And while it's passing, it'll pass, this is a proton, by the way, not a proton, I'm sorry. But it'll keep passing, the gluon will keep going from quark to quark to quark, and thus will create, there we go. And it thus creates a situation where it's always color neutral. That's what they always want to achieve. So that's why they are bound up so tightly in hadrons. So I said 4 fundamental forces, and we all know gravity. But gravity is not so easily explained by the Standard Model, unfortunately. They have a theorized boson that would describe it, but called the graviton, but there's no experimental evidence for this. And this gravity is definitely a fundamental force, but there are also other theories like Einstein's general relativity that can describe gravity. So there's more work to be done on that one, but that's also another question that looking into physics like this can answer. But it doesn't matter for particle physics. Good, that's good. Because gravity is very weak compared to all of the other forces. And with looking at these tiny particles, the masses are so tiny and the velocities that they're traveling at are so high that the effects of gravity actually just fall within the margins of error. So we're good. So emerging with the Standard Model was a set of rules and mathematical equations to describe how kind of everything in the universe behaves, called quantum mechanics. Super duper complicated, but one of its founding fathers, who I think is the most important but least known physicist ever, is Paul Dirac. I would be surprised if any of you have heard of him. But he, among other things, he developed the Dirac equation, which had a really interesting result. Whenever he would solve it for a specific situation, he would get 2 answers, much like you get 2 answers when just solving a quadratic equation. And from this, he predicted that there was another type of matter out there called antimatter, and where every particle that I talked about that was in the Standard Model would have a corresponding antiparticle with exactly opposite properties. Exactly, if it was a positive charge, the antiparticle would have a negative charge, and when those 2 particles met, they'd be annihilated into pure energy. And he was right. Only just 4 years after he hypothesized this, they found evidence for the anti-electron, which they call the positron, positive charge. And so we can see some evidence for antimatter in this early photograph of particle decay. So a particle would be coming up this way, and it would decay into a electron and an anti-electron. And we can see this because there was a magnetic field in this experiment, and so the moving charges would curl and bend, but since they have opposite charges, they would bend in opposite directions. Yeah. So now you might ask, how do we know any of this? I've said before that experimental findings confirmed X, Y, and Z. But how do we perform experiments on things that are smaller than we can see? Well, physicists have figured out that a good way of detecting these particles and looking at them is just really smashing them together really hard and just looking at the result, looking at what products decay from that smashing. So they take two focused beams of particles, speed them up to velocities near the speed of light, and then smash them together, and then they'll decay, and we can detect the decay products. One place that this happens is called CERN, which is the European Organization for Nuclear Research, and it lies underground beneath Geneva on the Franco-Swiss border. And CERN is just an acronym for this, but in French, by the way. So this is a map of the facility, and as you can see, it's huge. Like, this is a city, and then the giant circle is where they speed up particles to near the speed of light. And then they smash them together in these red dots, which are the detectors, and there are different detectors along the path. And that's where they can detect what happens. This experiment that I've been looking at specifically for my independent study project is the CMS experiment over there. And that stands for compact muon solenoid, and that's because it was designed to look specifically at muons, because they didn't really have detectors for that before, but it doesn't only detect muons. So let's look a little bit more specifically at the CMS experiment. So first two things we noticed about this is that A, it's really, really big. Look at if you can see, I don't know in the back, but there's a little person standing right there, and to provide the scale of how huge this detector is. And also it's really complicated. There are a lot of parts because different particles need different detectors to see what's happening. So I'll just tell you a little bit about the structure of it because this is what I've been working with a lot. This white circle in here is called superconducting solenoid, and that's basically just a fancy way of saying really big magnet. So the reason that they have that is that they can tell if a particle is charged or not based on if it bends and which way it bends, and how much it bends can provide calculations for energy and momentum. Another part of the detector are calorimeters. So calorimeters just measure energy, and they can also, based on their data, measure the position, like where it is. So I think it's interesting how they work, so I'll just tell you. So as the particles, as the beam of particles smash together and then decay, there's like a burst of particles out this way. And as passing particles go through the calorimeter, it hits atoms that are in the material of the calorimeter and will excite their electrons. And then so those electrons will be excited as it passes through, but then they'll relax and emit a photon. That photon is just light that can be detected and then sent to analyze. But the amount of light that's generated is proportional to the amount of energy that the passing particle had. So in that way we can measure exactly how much energy the particle had. And there are different types of calorimeters with different materials based on what different particles will interact with, and that's part of why it's so giant. You need a whole bunch of different stuff. The big part on the outside are the muon detectors, and it's a really important part of this one because, like I said, they didn't really have a way of detecting muons before. They built this detector. So muons, if you remember before, they're a type of lepton, and they're like electrons, but they're heavier and they don't like to interact with things very much. So again, that's part of why the material's on the outside, because the muon would pass through all the other detectors and materials uninhibited. So the muon detector works in similar ways as the calorimeter, but instead of it'll hit the electrons, the atoms in the muon detector material and actually knock the electrons that are in that detector's atom completely off, and then that electron will hit other atoms and then knock those electrons off, and it'll create like an avalanche of electrons, they call it, and then that signal can be picked up and analyzed for calculations like momentum, position, energy, etc. So this is just a little bit of how the detector works. So we've all seen this equation before, Einstein, E equals mc squared, but it has really profound meaning here. It's that mass and energy isn't really so separate. So as particles are smashing together really fast inside this experiment, they have a ton of kinetic energy. So in this way, particles that emerge from this decay, the decay products, may actually have more mass than the original smashing particles had, because some of that kinetic energy was converted into mass, which is very interesting. But also, interestingly, if you just look at a hadron, which is like a proton, most of its energy is not from the actual quarks inside of it. Most of its mass, is from not from the quarks inside of it. It's from the potential energy that's bound in there, which is very, very interesting. So here's another view of the detector, and this is the kind of view that you can use to actually visualize more realistically where the particles go. So we'll just go through this a little bit. So if you look at a muon, this is the path that a muon would take, and the blue highlights here are where it would be detected. So the fact that it's wavy is because muons are charged, and the magnetic field causes them to curve. And that curvature can be used to calculate calculate things like its momentum and its energy. This is what it would look like if an electron was immersed, and it would stop in the electromagnetic calorimeter and again it's bent because it's in a magnetic field and moving charge. This is what a photon would look like. If a photon does not have electric charge, it's not a bent path. This is what a charged hadron, so that's a grouping of quarks that's charged, would like a proton would look like. That's the decay product. That's the decay half of that particle. And this is what a neutral hadron would look like. Again, it's neutral, so path straight. And I know I sound repetitive, but it's really important in the data, things like this. Like its path and it's bending. So this is what they're doing at CERN, but what am I doing with all of this? I'm not in Geneva, obviously. So for my intense study, I've been looking at, first after teaching myself, all of the preceding information, and but much more in depth. I'm looking at the data that comes from this CMS experiment and trying to perform my own analysis on it. And this is really exciting for me because this is exactly how physics is developed, by testing theories and just looking at a bunch of data to confirm or deny it. And that's really cool for me. So I created this histogram, which is it looks simple, but it actually takes a lot of pouring over a lot of data and analyzing that data correctly and understanding what all the numbers mean. So this histogram is about the mass of Z boson. So I looked at a lot of different events, different decays of the Z boson, and reconstructed its mass to get a histogram. And clearly, the most common one is about 91.592, and that's really accurate data because the standardized mass for a Z boson is 91.2. So that's pretty good. And so yeah, so that's what I've been doing. But physicists at CERN aren't making mass histograms all day. So what are they doing? Well, the physicists at CERN are answering questions that are really big, really broad questions that they can look at specific data to try to test theories and about these broad questions and see if their data confirms it or denies or invalidates it. So one interesting question is, what is the universe made of? Well, astronomical observations have concluded that there's some mass out there that we can't see. We don't see it visibly, but we can tell that it's there because of its gravitational effects. It's making galaxies rotate faster than we expect that they should, and it also makes light bend from stars that are really far away. So we call it dark matter because we can't see it. But what makes up this dark matter? What are the components of it? Well, in CERN, the CMS experiment, we can test theories. We can create conditions that would test different people's theories about what makes up this dark matter, and maybe make some of our own dark matter. So that's one exciting question that the experiment can answer. Another question is, how many dimensions are there? Well, we all like our standard 3 dimensions, this way, this way, this way. But, and then it's also widely accepted that time is like a 4th dimension. But there are theories, like string theory, that are attempting to unify all the fundamental interactions, the fundamental forces. But they require more dimensions. Some of them require as much as 11 dimensions to work. And this is really inconceivable, but that's how the math works out. Their explanation is that all these dimensions are curled up really, really small so that we don't interact with them on a daily basis, but that they're there. So how CMS the compact muon solenoid experiment could start to answer these questions is we can get really, really, really high energies in this experiment. And so those high energies could provide enough power for those particles to actually move in and out of those dimensions. And how we would see that is by a particle suddenly disappearing and then suddenly reappearing again, and that moves through that fifth, sixth dimension, which would provide support for these kinds of theories, which is really, really interesting. Another question that CMS can answer is, what were conditions like in the Big Bang or right after the Big Bang? So like I said before, quarks are confined in hadrons because of their color charge and their desire to be color neutral. But at the really, really, really high temperatures, like that right after the Big Bang, the strong force is not strong enough to hold together those super high energy quarks. So what emerges is this quark gluon like dense soup that they predict is what the conditions were like right after the Big Bang. And actually, every year the CMS experiment creates conditions like this, such high energies, such high temperatures, that they can create their own quark gluon plasma and study it. It's in very small quantities, but they can still study it. And so then they let the quark gluon plasma cool in the same way as it cooled in our universe. And then they can study it and answer questions like, why do we see our world dominated by protons and neutrons as the hadrons? Why don't we see the pion all the time, which is another type of hadron? So they can study that kind of question to answer, why is the world the way it is? And so that's really exciting. But I would say the overarching goal of the CMS experiment, and really all scientific experiments, is to just push the frontier of our understanding of how and why everything. So thank you for listening to my talk, and I will gladly answer.
So when you're talking about them possibly like confirming or denying whether there are extra dimensions, by seeing if the particle like pops in and out of existence, I guess. If a particle, let's say there are 11 dimensions and we only observe 3, if it like, how would it moving in say dimensions 4 through 11 make it disappear from the ones that we can observe? Because like if I move my hand in a one-dimensional line, like it's still there, doesn't disappear.
So imagine like like you're walking on a tightrope, and you only really have one dimension. You have this way or you have this way.
Yeah.
So what if I'm standing here and you see me, but then I jump over you and go over here? You don't see this because you're only looking at this one dimension.
Yeah.
That's what it would be like. They would be jumping over the dimensions that we can see. This is really we only can imagine 3 dimensions really. So you can't extrapolate it very much, but it's like I'd be jumping over the dimensions that you can see into and like disappearing and reappearing essentially.
But like how, if the dimensions are so compressed?
Yeah. Well, the energies is like I said, the high energies of the
they allow it to sort of.
They expand it. If it's tiny ball, the high energy like pries it open.
I see. Okay, and then another thing. So in your histogram, you got like different values for the mass of the Z boson. Is it supposed to just like every Z boson, like for example, like a proton, they all have the same exact mass because they're all protons? Is that just like due to a certain like experimental errors or?
Sort of. So how I got these masses is how you get the mass is by collecting all of the data from the decay, and then summing up all of their energies and converting that into their mass.
Yeah.
And so it's an approximation because you don't get everything. The CMS detector can't detect, for example, neutrinos.
Yeah.
So you either lose a little bit of mass, which is why there's more over here, or you detect something you're not supposed to, which is why there's more over here. So that's but the majority is this way. And like I said, it could have more kinetic energy or potential energy, so you don't measure it exactly perfectly. And also in these kinds of experiments, we're looking at things so tiny, that the margins of errors are really large.
Okay.
Well,
Two questions. One, the tightrope analogy. Would you be considering time travel since time is the fourth dimension?
I mean, time travel is not complete. Like time travel can be accurately described mathematically, but it's not feasible. Like, you're not gonna. Sorry.
And two, I don't know if this is true or not, but I've heard that gravity can travel through the dimensions.
That's above me. I don't know.
Cool.
Any questions? Amanda.
I don't know if like this is at all related, but for the CMS, how do they isolate because they're so absolutely small, like how do they isolate them so that they can like shoot them?
How do they isolate? Oh,
Like
how do they
they
get the particles to?
Yeah.
Well, through they can use different things, but pretty much they speed it up really fast using like magnetism, and only in a way that only the particles with the correct conditions, with the correct speed, with the correct mass, will follow that path.
Okay.
Anyone else? Yeah. Okay, so that was my talk. Thank you all for coming.
Yes. And if you have more questions, you're free.